So for part D, we want to generate 50 points of synthetic data of the previous two tanks in a series for 15 seconds and add a normally distributed error around each value with a standard deviation of 0.02. So to do that, we are going to first start here, and we're going to start with our T experimental. And our time, and this is going to be equal to np.lin space from 0 to 15 seconds with 50 plots. Next, we are going to name our transfer function, and this is just going to be a repeat of what we already have, but I'm just going to repeat it up here. So I'm going to call it of our process. So we're not multiplying it by our PID controller anymore, so we're just multiplying it by the process. So I'm going to go ahead and copy this and set this equal to that. And then below that, I'm going to, so this will give us a function of time and our height. So our time just doesn't matter, so I'm going to put that as an underscore. And then we want our H2 experimental. And this is going to be equal to our TF process dot, it's a step function from and time, the time is equal to time exp. Okay, and then next we're going to want to plot this, so I'm just going to go down here and I'm just going to copy this so I don't have to keep retyping it. I'm going to add that here. Our x is actually TEXP, and our height is H2 EXP. And then this is actually in mode equals markers. We have to do that if it's experimental. And so if I plot this, so it looks like this, but it looks really clean. There's nothing wrong with it, and it's just not, this doesn't represent actual data. So if we want to do that, we would come up here and we want to generate random numbers around a normal distribution point at a certain standard deviation around each of these values. So instead of it being exactly here, it's normally distributed around somewhere around this value. So it gives us like a little bit of like an actual data set. So this will be RNG equals np dot random state 1, 2, 3. And then down here below, this is where we're going to set our standard deviation. So I'm going to do H2 EXP equals our veg dot normal with our location equaling our H EXP. So it's just all of these numbers. I'm just setting it equal to that. It could be set to a specific location. I don't want that. I want it to happen over the course of the whole plot. And then the scale is going to be our standard deviation, which we have is 0.02. So then if I oh, I did this as, I'm at RNG. Oh, this needs to be a 2. Okay, now let's try this. Okay, so this just gives us random, so it just gives us more of like an actual data set. And every time I run this, I'll rerun this. It'll give us a different one every time. So this just looks more like an actual data set, and that is D1. Okay, so here we have Question D1. And basically we want to fit the data from D1A using a FOPTD model, which is first order plus time delay model, by minimizing the sum square error between the model and the data. So to do that, I want to show so I want to show what this graph kind of looks like before I put it out into Python. So with all first order, we have this where it kind of goes like this. This is like our higher order functions that have this like little. It doesn't. It's not like a steep drop. It kind of has this like this knee, I guess you could call it, and this. So what we want to do is we want to approximate this in terms of a first order. So we can do that by using this equation. So a normal exponential at 0 would just be, it would start right here, would just be k 1 minus exp times over tau, and it would just be that. But we want to shift this by, it would just look like this. It would go like that. And it shifts. We want it to shift. So hold on. Let me back up. So this right here, it would do that at any given point of time. At any time, and we want to shift it, and we want to shift it by the means of theta. So this new equation becomes k, becomes, you can, okay, wait, there you go. Becomes k 1 minus exp, and we're going to shift this time, minus theta over tau. And value is the ratio between the change of the output in relationship to the change of the input. I don't know why this isn't updating. But basically, yeah, I have right here k is 1, k times 1 minus exp minus theta over tau to approximate these functions. And I will now go to my coding. So now to code this, we are going to define our function, which is f of order plus time delay. And this is in terms of v. And we have our k value, tau, and theta, that all equal v. And then our y, and our k by our 1 minus jnp dot exp, and this time value is actually negative. So I think in my other video, I think I said that it was, I think I forgot the negative. So that's actually negative. And then we'll have our time experiment, and then this is divided by t. Oh, it's actually txp minus theta. divided by tau. Then next we're going to return J and P. And this will be where our time experiment or time is greater than our theta, and if it is, if it's not, then it'll input 0. If it is, it'll input y. So we got that. And then we're gonna want to plot this. So again, I'm just gonna copy this. Oh, okay, that didn't copy. I'm going to copy this. And we need 2 of these. So big dot add scatter. We have one for our model and one for our plot. So we have x equals time exp. Up here is also time exp. And then y is equal to, oh, hold on. We have time equal exp, and then we have y equal h exp, and this is the model, so we are going to call the mode markers. So mode equals markers, and then this down here, y is going to be equal to our FOPTD, and we're going to need a v-guess. We're going to want to guess our gain. So I'm going to come here and I'm going to do v guess, and I want to guess our gain was, maybe about 2, and then our time constant, which is roughly, we can guess around 3. And then next we want to guess this little portion, what we think this delay is, and we can guess about 1. So I have this v-guess, so I'm going to put that here next to my FOPD, and then my mode equals lines. Okay, and then we'll go ahead and plot this. Oh, I need, I don't know why that did that. Let's try that. Ajax. I keep doing that. Okay, now let's try this. Oh my gosh. This equals to, oh my gosh. Okay, now let's try this. Okay. That's not right at all. Let me go up and look at this one more time. Oh, okay, wait. This needs to be the other way. This needs to be like that. Oh, much better. Okay, so this is fitting the data. This is this line for the FOTPD. No, FO